When is device Hello, sorry to be late, everybody. Still just barely hot in here. Do you know when you're going to post homework 4?
Homework 4?
Yeah.
Like real soon.
Okay. It's just a few other professors are posting a whole bunch of stuff at the same time.
What's that, sorry?
Oh, just a few other professors are posting a bunch of stuff at the same time trying to...
Yeah. Those professors, they just make everything.
Well, the problem is, like when everyone synchronizes all the deadlines, and then... It makes the whole scheduling a little bit scary.
Okay, so let's see. Questions, anybody? Tomorrow, homework 3's due. Is it going okay? You're a little sick of taking the derivatives of stuff? That's really what neural networks are all about, right? Like I mentioned this earlier. Really, it'd be fun to kind of take some time to think about it. But this course is not really designed for that. But this is a kind of programming that is sometimes it's called differentiable programming. Right? Like we're not writing explicit code to say recognize the objects in these images, but we are, we're basically writing kind of like a kind of program that can find the right way to do that, given all these, all this data, all these examples, and so, hopefully you like calculus, or at least taking derivatives, because that's like the whole of it, right? And some linear algebra, taking lots of matrix multiplications. We talk about a lot of like little, like lots of little details about how modern neural networks look, but in the end, there's just a bunch of linear algebra and a bunch of derivatives, and somehow it all works, which is pretty cool. So any questions as we get started today? No? All right, well, let's see. I'll try my thing where I always get this wrong. Yeah. And turn this one on. That one on. There we go. Okay, so this is going to be our part 2 on transformers. So we talked about transformers last time. This kind of wild, yet like wild on one hand, and yet pretty simple on the other hand. Idea of how to solve this neural machine translation problem. How to take a variable length sequence as input and output another variable length sequence, and to have that be, to do something very useful like translate from one language to another. And today we're going to continue on that and talk about a little bit more like how transformers are like kind of like the approach that's being taken with transformers in terms of just general natural language processing or understanding, and in particular, just kind of like just like the approaches that are taken, like the way that you train these things, say on like really large data sets. Along the way, we're going to look at a couple of like the more modern examples, things like the family of GPT models, 1, 2, 3. Some related types of models like BERT, like a family of BERT models, and like T5, things like that. You might have heard of if you've been paying attention to this. It's the news in this area. Okay, so we basically spent the last lecture going through this whole architecture. Yes, the details of like the multi-head attention are a bit, there's a lot to it, but really these are pretty simple networks in the sense that like you have this very simple block that you just repeat a couple of times, or however many times for your encoder, and then you have something almost the same, just this additional, like instead of having one multi-head attention, this additional one that looks pretty much like this, except it has this masking. Actually, I added the slides to kind of just illustrate that masking, but do this masking so that when we do the decoding, we're not looking at any, like if we're in a language that reads from left to right, we're not looking at any tokens to the right of the token the position in the sentence that we're trying to translate. And then we have this multi-head attention, a second one where the keys and the queries come from the encoder. Simple, fully connected layers, simple residual connections, and you just kind of repeat these modules over and over and over again. So pretty simple in design. And then importantly, we mentioned this, we talked about this a bit at the end. You can think of, each model that we've looked at, there's some kind of inductive bias, as it's called. Some kind of like expectation of the data it's going to work with is like built into the architecture itself. And so like when we're doing convolutional networks, the inductive bias there is that we expect, local statistical correlations to be very important for understanding the data, to understand what's in the images. And it's building that up through like layers and layers where we go from local to like more and more kind of global features that that works. Like the inductive bias there is that the idea of the convolution, and in the RNNs it's this inductive bias of like there's information and learning how to go from one token to the next. in the sequence. Transformers can do the same thing, but we have to kind of force it to happen. Maybe let's go straight to this slide. We kind of have to force the like left to right thing to happen because in reality, like every bit of the input, every token that goes into each encoder layer is interacting in that layer, through this self-attention, which is just a bunch of matrix multiplications and dot products with everything in there. So it's all fully connected. So like there's this, the inductive bias here is not very constrained. It's a lot less constrained than say like convolutions or in RNNs. And then in the decoder, we have to like kind of make up for that and mask out the ability to use the tokens that are ahead of any one token, because you shouldn't have that ability at decoding time. So that's kind of interesting, and an important part about transformers is that they seem to have a far more general inductive bias. Are you going to ask a question?
Yeah, so doesn't that make it like squared? Do n squared number of...
Yeah.
So isn't that really bad for doing a forward pass? Because previously it was almost constant time.
Constant time with what? Like you have to think about what it is you're looking at. Like it's n squared with respect to the input in terms of like the number of weights.
The sentence length.
Yeah, right. So number of tokens. So yeah. So like memory would grow, n squared, that kind of thing. It turns out, if you remember, I don't have the slide this time. Looking at the slide from last time, these were actually far more efficient in terms of reaching the same kinds of levels of performance on blue scores, because while there is like there is this kind of n squared dependence in terms of like memory, in terms of number of weights. Also, like as a result, like the flops would grow that way as well. Per layer, you have far less layers that you need to include in these networks to get the same performance. So yes, there is that dependency, but it turns out that you can actually have very, very long sequences despite that kind of dependency on the length for memory and flops. However, at some point that is going to become a problem, even with very modern GPUs and modern approaches where very, very large transformers they're not all held on one GPU. Like different parts of them are on different GPUs, and then when you do this forward pass, you're having to do this communication between GPUs passing data from one to the other as you run this forward pass, and the same thing with the backward pass. So at some point that becomes a problem, and there are lots of versions of transformers that try to reduce that complexity. So there are approaches that reduce that to like n log n instead of n squared, and there are approaches that reduce that to just n, they go n, n being the length of the input. The simplest way to think about that is there's these things called axial transformers that have complexity of big O n, simply because they do like a kind of like a row-wise interaction, and then like a column-wise interaction. So it's like a factorization, like an outer product factorization of like the n squared matrix interaction. You only go like one direction and then one direction in the matrix in terms of the interactions, and then you put those together, so you have this 2ON, but that's far less than n squared, and seems to work pretty well. And that's really similar to like, I don't know, there's lots of variations on that. But yeah, it is one of the considerations. But in general, these are less expensive to get equivalent performance than say like big RNNs or something like that. But great question. Coming back to this, sorry. I wanted to use that because I was talking about that, but so we learned this last time about transformers as neural machine translation systems, and this is kind of like the schematic of the whole thing put together. By the way, one thing that I think might have been a bit confusing as I was going back to the slides, realizing just this is a little bit weird. I just want to point it out. I don't think anybody asked a question about it, and I don't think I pointed it out. But when you're doing the decoding, there's still an input to the decoder, part of the transformer, and in this neural machine translation a task, what you're doing is you're trying to get it to do like what we were doing in the RNNs, where it's going to output the translated sentence, right? And we have these start sentence and end sentence tokens to indicate to the network hey, we're starting to translate now. Right? We think we should end the translation. And then in these slides, these diagrams that I told you I pulled from the Illustrated Transformer. It's a great post, hopefully somebody went and visited it. They look like this. It says previous outputs, but it looks like this. Really, there should be, in this, and I just kind of try to indicate it here, there should be a start of sentence token right here saying, we want to decode, we're telling it, hey, we have a start of a sentence, you're going to have all of the context from these encodings of these tokens to use in the decoder. So produce the first token, and then you produce the first token, just like in the RNNs. These are going to be classified on the vocabulary. It's going to output a token. You take the most likely one from that, and then that becomes input for the next token that you run through here, and so forth. Right. So that looks very much the same. I don't know that was clear or not from the discussion on Tuesday. It probably wasn't clear. I just wanted to make that more clear. But yeah, this is neural machine translation. So transformers come out, show this wonderful performance on neural machine translation, and with less computational cost. Great. So what? What's the big deal? We have just another neural machine translation. It's already pretty good. Well, what's the big deal? Well, after that paper, there was a lot of interest in trying to figure out what you could do with transformers, and that's coupled with this long time desire to have machines that are really good at just understanding language. So neural machine translation is one of the tasks around that are interesting in language. But there's of course a whole bunch of other tasks that are important for language that you want your machine to be good at. So we've been talking about the BLUE score for a long time. There's a more kind of general, it's even in the name, general way of thinking about evaluating machine language systems for just general understanding. And one of the very popular methods for that, or metrics for that, is something called BLUE. This stands for General Language Understanding Evaluation. And it's really just a collection of a bunch of tasks. There are 9 tasks in BLUE. There's actually now Super BLUE, which has more tasks and it's larger corpuses and things like that. But this is kind of well accepted over the last couple of years. This BLUE. And what you have is just a bunch of a bunch of data sets and tasks on those data sets. So you have this COLA data set. It says the task is acceptability. It's basically it's a large data set. It's got about 10,000 examples in it, showing you the split of train and test. But it's basically examples of is this a grammatically correct sentence or not? That's what acceptability is. So like a binary classification, yes or no. So that's a task. If you have a good kind of general language understanding system, then it should be able to tell if a sentence is grammatical. This data set, SST2, is about detecting the sentiment. This is actually just movie reviews, taken from the web. So someone goes through and says, yeah, this is a positive review, this is a negative review, this is a neutral review, and you have a classification problem as another way of evaluating whether this thing kind of understands the content of those reviews. You have a whole bunch of other tasks. There are a couple for doing what's known as paraphrasing, so being able to like take a large corpus and like tell you, be able to summarize it essentially. Tell you what the constituent parts of that are. There are other corpuses for doing things like sentence similarity. It's basically like two different sentences that have the same semantic content. You want your machine language system to be able to say yes, they have the same semantic content or not. You have other ones. These NLIs. This is natural language inference. Yeah, inference. Where this is something like entailment. So you have basically like two sentences. The first sentence makes some sort of statement about the world, and then the second sentence is like the task is to say, does that second sentence is it entailed by the first sentence? Like, does it follow from the first sentence? Can you infer it from the first sentence? So again, it's like a kind of classification: yes or no. Can you do that? There's question and answering corpuses. This is more inference. And you can see that, like the domain that each of these come from. So some of these are just scraped from Wikipedia generally. Some of these come from works of fiction. We saw movie reviews. I think this is from Quora. This question and answering is from just scraping Quora. So just like a bunch of different things, right? So whether or not this is like the perfect way of evaluating, it's hard to say. I'm sure it's not perfect, but somebody did the work of putting it all together, and now lots of researchers just use it as a way of saying, like, how good is our system at like understanding language by evaluating how well it does in these tasks. Cool. So how do we go from a system that does really well at translating between languages to being able to perform well on a whole host of other language tasks? And that's really the content of today in terms of like how transformers are used to do that. Any thoughts before we get going? I mean, some of you might already know kind of what's going on here, like how this is done, but any thoughts on how you would take a system like transformers and do something like this? By the way, it's not good enough. You basically want one model to be able to do like all these, right? Like not like one model to do this thing or another model to do that thing. You want like one system that can do it all. Anyways, any thoughts on that? What about as you're thinking about that, what about transformers can be used to do other tasks like this? What are we getting out of transformers that would allow us to do well on tasks like this? Yeah.
So you're going from like natural language to some artificial language that you do know how to answer?
And like artificial language how?
Like for question and answering, questions could follow like some really standard form that you could just apply it to a database, like you're turning human questions into SQL.
Yeah, so like you're using the word language there to kind of represent that it's like some system of relationships between tokens or something like that.
Yeah, so it's almost like going from English to SQL, and then you just run the SQL against the database.
Yeah, I think that's a good intuition for sure. I think that's a really good intuition about like how we might use these things.
Or Prolog, maybe.
Yeah, I think that intuition is good there. Any other thoughts? Remember what's happening here. What's happening in the layers of the encoder and the decoder and things like that. So we motivate that by thinking about word embedding. So we haven't spent any time talking about word to vec or glove, but I mentioned it before. We also mentioned byte pair encodings, which are typically used like in transformers to do the encodings. But there are these ways of learning to like assign a vector to different tokens in your vocabulary as a way of like being an encoding or embedding, as it's often called, some version of that word. The thing about like word to vec and glove is it's something like it's context free in the sense of like there there are words like bank. There are many, many words like this in English, but there are words like bank here, which have multiple meanings, right? There's a bank where you store your money, and there's the bank of a river, which is some sort of boundary of the river. The only way you know which bank you're talking about is in the context of all the other words around it, right? That's the only way you could tell. And these word embeddings, like things like word to back and glove, that learn a kind of representation that depends on just how often various tokens kind of co-occur in like short engrams. There's some notion of them being by each other, but in the end, there's a single vector that's produced. That means, like in the case of bank, would need to both represent its usage in a sentence like this and in a sentence like this at the same time. So it's context free. In the end, doesn't really take into account at runtime take into account its context. So that's problematic, right? If we want to do really well in understanding language, programmatically, algorithmically, we're going to need to have better embeddings that can take into account the context. And that's exactly what the models that we've been talking about lately do, right? So here's some fancy representation of a simple RNN. There's our transformers again. Remember, what's happening here is that there's this notion of like transforming our inputs into some hidden state that depends on, in the case of RNNs, the previous hidden state, which itself depends on the previous hidden state, and that's the recursive part here. So if I put so season here, season might have a couple of different meanings, and the encoding that I get for it here, when I input season into my RNN, is going to be different depending on what words came before here. In general, that can happen. So I'm getting a contextualized embedding for the word season. Notice, because of the inductive bias of recurrent neural networks, that it can only depend on just the things that came before it in terms of the encoding, in this very specific way of stepwise building up the aggregation or building up the context. As we talked about a bunch last time, transformers are doing the same thing in the encodings, except that, at least at the encoding level, not the decoding level, but at the encoding level, the embedding, as you run through each of the different encoder layers, like the code or the embedding that comes out of that layer depends on all the other tokens in that phrase, right? So it's not just the ones from before, but because we allow for there to be all connections in the encoder, you get to understand that word, the meaning of that word in the whole context of that phrase, or the whole context of the document, or whatever, as however long the input is here. So there's a huge advantage here over the other approaches to representing the meaning of the context, or not the context, but representing the meaning or the content of each of these tokens when using these kinds of models, because of the ability to take on context. So the point is if we now use these kinds of embeddings to these representations of our tokens to do these other natural language tasks, we should do a lot better. Again, because they're taking into account context. We should be able to do way better, actually, and you do. But the question is, okay, fine. What's the right way to then learn these embeddings? What's a general way of learning these embeddings? And that's where all these other models that you've heard about that are so famous now, they're all kind of solving this problem in different ways. So, for example, a couple of years ago, And you can thank Elmo for I think starting the whole process of there being like many different kinds of language models that are named after Sesame Street characters. I think Elmo comes first. Then you have Bert. There's Ernie. There's a couple of other ones. I don't think there's a Big Bird yet or anything like that, but and OpenAI just sort of bucked the trend and just gave it. Actually, in their first paper, they didn't even name it GPT. It's sort of, it was not even a name for the model in the paper. Just people started calling it GPT because of like what it is, and then that stuck, and then they used that data. But anyways, you get this kind of funny relationship to Sesame Street. But there were a couple of first, like the first iteration of doing these kinds of contextualized word embeddings for doing natural language understanding generally. These are things like Elmo, GPT, and BERT. Do I have the Elmo slide here? No, I don't think I do. I'm not going to spend any time on Elmo. I'll just tell you that what Elmo does, Elmo gives you a contextualized embedding for your tokens by learning two LSTMs. One that takes that takes your sequence in the correct order, and then it reverses the order of your input phrase, and then creates an embedding for that token when you feed in that phrase in the reverse order. So it's kind of bi-directional thing happening here. You get two embeddings for that. You concatenate those, and that becomes your embedding from the LSTMs with the contextualized word embedding. So kind of remember, by construction, LSTMs can only provide the word embedding in the context of what's come before it. So in order to kind of get both sides of the phrase for that word, you do this correct order and then reverse order. So two embedding, concatenate them. That becomes your embedding for then doing like other tasks with those embeddings. But these other models use transformers, and that's where we're going to focus today. So in general, the approach that's taken here for all like the transformer approaches is to do this. Is to approach this through what's being called pre-training. So pre-training is exactly what it sounds like. It's training that comes before. It's pre in the sense that the tasks that we actually care about doing, that we're going to evaluate ourselves on, we're not going to be training to do those tasks directly. What we're going to do is we're going to pre-train, some kind of transformer that's going to learn the distribution of language, attempt as well as we can to learn the full distribution of language, and then we'll use the embeddings for those words to then do these other tasks through a process of fine tuning. So the pre-training is we have to pick a kind of approach to how we do the pre-training. But the idea is, again, very, very generally, we might be learning, if we're thinking about learning the statistics of language, might be very generally learning how to, say, very accurately produce the next word or next token in a sequence, given the sequence. You'll see as we go that there's a lot of ways that we approach pre-training that are not just this straightforward. But remember, in general, what we've done so far is to do something like that, and that's quite a powerful model just in terms of having appropriately representing tokens. And then what we do is this process of fine-tuning on the tasks that we care about. So we're going to do this pre-training. We're going to learn the distribution of our language in some way, and then, for example, what we might do is take the decoder from our transformer. We'll talk about this in just a second, and fine-tune it so that it can do something like sentiment analysis. So using the rich information in the embeddings of the words, but then just doing But then just training it to say like, okay, what I really care about is from those rich embeddings, from those rich featurizations, contextualized featurizations of our words, like do sentiment analysis. And it turns out that this is super powerful and gives you state-of-the-art performance on basically all language tasks. And now, all these other models we're talking about, GPT, BERT, T5, they're all like different ways of doing this pre-training with different parts of the transformer. Why should this work? You know, like most things, you try it and it works. Like most things in neural networks, you try it and it works. And then you come up with a story afterwards about why it works. But maybe it's not too hard to to believe, right? That the pre-training task has a kind of loss to it, which is evaluation of how we're doing on that pre-text or the pre-training task, given a set of weights. When we do the pre-training, that we're trying to find a really excellent set of weights for that model. Then we do fine-tuning. We switch losses. We switch losses. We hope that it's somewhat related because it's still language, but we switch losses. And then we try to minimize again, but we're going to start at like the weights that we learned during the pre-training task. Right? So the whole point of pre-training is to get us to some great set of weights that we now start from to do the fine-tuning. And why might this work? Well, maybe it works because this set of weights is just really excellent for the language. That's probably the case, right? Like if we've learned the distribution of the language, then these weights encode that, and now all the other tasks are just somehow like nearby that, right? So like you change the loss a little bit, it's going to change where the minima, like the nearest local minima is, or minimum is, and then we're going to have an easy time of going and finding it. Again, this is just like human story on top of like the observation that this works, but it's probably right.
When you do pre-training, are you forced to use the same convention with weights as in the pre-training model?
When you're doing the fine-tuning?
Yeah.
Yeah, you'll see some examples, and I think we'll explain this. But yeah, the basic idea is you're gonna use most of the network, so most of the weights, to do the fine-tuning task, and then maybe you're gonna add like maybe a couple of layers or something like that to then allow you to go from those word embeddings to some output that's appropriate, say like for a classification task, like sentiment analysis. But the majority of the weights are going to remain the same. Well, the majority of the networks should remain the same. And so yeah, so that's where the story comes from. Good question. Okay. So what can we do? Well, it kind of depends on what part of the transformer we're going to use in the task. So the kind of pre-training we do is different if we're going to, say, use the decoders from a transformer, like the decoder. It's different if we're going to use the encoder, and it's different if we're going to use both. This might seem a little bit weird at first, but you'll see as we start to look at the examples, like what we mean. We'll start with the decoders first because they're like the easiest to think about because already our tasks have been supervised at the decoder level. Any thoughts on this? Like what's going to be weird about, like say, just using the encoder to do the fine-tuned task? Like what's weird about this?
What's the output?
Yeah, what is the output? Like what? The output is just a bunch of like for each token that you input, there's a final like encoding or embedding of that. So like in general, how are you going to train that encoder to be really excellent for understanding language?
Well, you could make the encoder, the output, the same as the input, and then you could probably like use this like as a compression algorithm.
Compression? Like maybe to compress it?
Yeah.
That's not a bad idea. I like that. That's not what's done in some of these approaches that we're going to show, but like, it's kind of a cool idea. Be thinking about that as we go here. All right, so we'll start with decoders. So obviously, these are, when we put the encoders and decoders together, we get really excellent neural translation models. And they have we kind of understand what comes out of them. So they're pretty easy to use for a couple of different kinds of tasks. So, for instance, when we start doing a task like this, we can just take our decoders, just pre-trained on, say, like the neural translation task itself, or what's really happening in these kinds of models is just to take the decoder part, and in a straightforward way train it to just produce for you the hidden state for the last word. So, like in a sentiment analysis, what you really want to be able to do is have one aggregated state that you're going to make a prediction from. And the decoders do this in a really nice way. Like they already kind of build this up because of the masking that you do on the last token, because everything else kind of came before it. So this is not too much of a departure, say, from the RNNs, although these are more powerful in terms of like how you can put these together, the depth you can create, that kind of thing. But basically, all you end up doing is to do the fine-tuning task is you just attach to this last token here, and this last encoding here, one or more linear layers, usually just a single linear layer, to be able to sort of translate from the dimension that you're in there to the number of scores you'll need for your classification task. Randomly initialize that, the weights for that, both your matrix and your bias. And then, just train the whole thing. Like, let all the weights, don't freeze anything, just let all the weights adjust to be able to do the best you can on that task. So, like, really straightforward, nothing too special here, and ends up being very, very good for these kinds of classification tasks where you're trying to predict a property about the phrase, like sentiment, like if it's grammatical or not, things like that. This is like the least interesting of them, but it is one of the ways that you can approach this. And there actually are no models associated with this where people are talking about them because of their power. Just because no one really cares how well you can do sentiment analysis, except for maybe if you are Netflix and you want to be able to quickly understand reviews. Yeah. So basically, one more slide that says the same thing. Okay. However, sorry, going back to here. However, you can train this. You can train just the decoder to literally do this to do this task right here, where what you really care about is producing the next token, right? So something that generates language, right? So for the things that classify on the last token, or the last embedding, okay, no big deal. It works really well. State-of-the-art kind of performance. But remember, this is still kind of an interesting task, right? This ability to produce the next token, the most likely next token given a sequence of tokens, because it's sort of amusing, right? We all kind of like to see machines sort of produce language that makes sense. And sometimes when it doesn't make sense, it's even more amusing. But that's kind of an interesting thing. And these networks are very, very powerful at doing that. And it turns out that like the first, like all generations of GPT are basically like iterations on this idea of just being able to take a bunch of input and produce the next output, use that as additional input, and then produce the next one, and so forth. And in 2018, when the first GPT came out, I already mentioned this, like GPT wasn't even defined in the paper, just kind of became known as this, so it's not even clear what it stands for. But probably something like generative pre-trained, transform the generative part being we're going to generate the next token given the input. It does remarkably well at like producing long spans of tokens of text that look like the most believable that we've seen in terms of like believable, I should say, look the most plausible in terms of like being actually produced by humans, like sentient humans who aren't just playing jokes on other people. So GPT-1 is good at this task. It's sort of like was one of many models. It really isn't until like GPT-3 where I think there's this kind of wow around like, wow, what can you do with GPT type models? But you get some sense of like what these networks are like, and these kinds of like dimensions kind of like they persist when you go find models in model zoos. Like these become kind of those standard dimensions that just like with ImageNet 224 being like the input size, the side length of an image. Things like dimension of 768 for the hidden states, and then when you do these feed forward, remember I was telling you yesterday, when you do the fully connected layers inside of a block, that second module, they actually expand out to be quite large in dimension, and then reduce again to be back to 768 because they need to be the same size so you can do the residual connection. Like the size of the corpus is fairly modest, 7,000 books. The vocabulary, doing that byte pair encoding, you get 40,000 mergers. So it's roughly that's a vocabulary of 40,000. And it works pretty well. So for doing this idea of like just generating language, just the decoder from a transformer is used. And remember, like again, like the slide maybe haven't pointed out, I just want to say it. We're really just training the decoder part here because we're not doing it like a neural translation task. We're really just trying to produce the next token. Okay. One of the really cool things that GPT can be trained to do in a fine-tuning task after you after you've trained it to learn to produce the next token is this task of natural language inference. Remember I mentioned that it's part of the glue set of tasks. And this is a really common, common type of task. So the idea is you're given this premise phrase, it says the man is in the doorway, and then there's this hypothesis that the person is near the door. And so what the network needs to learn to do is to this can be done a couple of ways. You can give it this pair. You can give it this pair, and you can say, does this does the hypothesis follow from the premise? Or you can train it so that this is your this is like your input right here. You tell it you're ready to start like the entailment part of the pair, and then have it produce for you a phrase that does follow from the sentence. And these models actually are really, really good at that. And it's not surprising because what it has to, so it already knows how to produce like the most likely things, the most likely next token. And then just from having those statistics, it now sort of, through the fine-tuning task, builds in the ability to then also say something that is entailed by the premise. So it's not the same task, but it's pretty close. and there's going to be some additional statistical relationships between like what you produce here and the things that it's seeing here, right? Like, it learned something about the fact that like the man and person would refer to each other here, and if something is in a thing, then it's going to be by a thing or is near a thing, and then the fact that like doorways have doors, that kind of those kind of things. So it's quite cool, quite cool. And the way that you do this is what's showing you here is doing these after at each of these. It's very much like all the other tasks that you're seeing. You're like producing the correct thing here is again just like classifying, predicting the most likely token to follow. So anyway, GPT, some one here is some generative model that does a really good job at producing producing sequences of tokens that like have good semantic content over long stretches of tokens. And here's just something to show that like in all these inference tasks that it performs at state of the art. Almost all of them, not RTE over there. Okay. GPT-2 is basically exactly GPT-1. It's just a larger model, and there's more data. And you start to get things that are pretty amazing in terms of like being able to take all of this as context, so actually quite large, bits of text as context, and then producing not only like plausible, text that sort of is related to here, but can do quite a bit of remarkable things. Like there's this kind of fictional context given here where some scientists are out exploring in the Andes Mountains and they find unicorns. So, I mean, it's been trained on a whole bunch of data where, unicorns might have were certainly in there, and something about exploring in mountains, scientists, all that kind of stuff. And then it produces text that really respects a lot of those ideas, right? Scientists do things like naming populations that they discover. They're named after something distinctive about that, about the thing discovered. And they said this thing about the horn being Ovid's unicorn. Then all of a sudden it becomes four-horned. So like that's not so great because unicorns would only have one horn, give it a name, but whatever. But if you keep reading through this, it feels very much like a news report, right? Like this is expressed kind of like as a news report. It starts off with this kind of clickbait and shocking finding, and so forth. And it persists that, and then it persists things like, so it's creating these very plausible names for scientists. It starts with doctor. Earlier, the title, it starts with its title. Remember, it was talking about the Andes Mountains, and it talks about being in the University of La Paz. So, like, very plausible in terms of like geographic locations. I don't know. If you just keep going through this and think about it, like to be able to produce something like this requires there to be a lot of understanding of the context, around this statement. And again, just learning, it's learning to do this just by producing the next token from a whole bunch of data and having a whole bunch of parameters. Okay, so that's a bit about decoders and how those are used to do some natural language understanding tasks. Questions about that? Oohs and ahs? Yeah.
So what do we use as the input to the decoders? Is it just context?
Mm-hmm. Yeah. You're like that sentence we saw, that context sentence. You literally input that, and then you start it. Yeah. So you would input that, and then that would generate a bunch of embeddings, and you take the prediction of the next. You take the last token, it makes a prediction about what should come next, and you feed that in as input, to get the next token, and so forth. So when you're training it, you're just training it like on shifted, or you're training it to, you have this input, and then in the training you shift the phrase by one. To the left, I guess if we're going left or right, like English, to predict the next token. That's it. That's all you're doing. And you have this other regressive masking so that you're only predicting from what came before. Now with encoders, we're going to do something completely different. In encoders, you don't have this masking, you're allowed to see all the context. That's what this says about bidirectional context, right? So our word is in a phrase, we have context from the left, context from the right, so the two directions. So what can we do with that? So the real question here is like, how do you pre-train a model here with just the encoders? Because you don't have this natural autoregressive aspect here. So like predicting the next token is a little bit like, it's kind of a weird, like unnatural task in this setting. What you want this thing to do is be able to, be able to produce embeddings that take into account the whole context. So like, what's the right task for doing this? And there's a bunch of attempts at this, and like the one that's become really popular and is really used as the starting point for like a lot of the natural language tasks that are out there, is this idea of BERT. So BERT stands for bidirectional encoder representations from transformers. Bidirectional meaning that we're using the encoder in both directions, like we just were saying. And the way that you train this is really quite interesting. You basically take a phrase, and you basically want to predict it, like you want to be able to generate it again, but you're going to corrupt that phrase in a bunch of ways. So here's like the standard approach, at least from the paper. So what you want to be able to, in general, what you want to be able to do is make predictions on roughly 15%. These are variable length phrases, so a percent's given here, so that's going to, just going to change with the number of tokens. But you want to predict about 50% of the tokens there from the following corrupted, so like of the correct tokens from the following corrupted version of the phrase. So you're going to do things like replace one of the tokens with just this additional token mask, right? So it's just like you're basically like masking it out. You're saying you can't know what's here anymore. Other times you always want to like replace it with a random token, so like a totally wrong token. That's kind of showed here, right? So like the phrase here is I went to the store. We want to predict about 50% of the tokens. So there's 5 tokens. We give it a 2. That's 20%, so about 15%. And we do that from a corrupted phrase. We're going to, for some of these tokens, we're going to mask them. And just say like, hey, we're just telling you there's something here, but we're not going to tell you what it is. And then other times we're going to just completely corrupt it. We're going to replace it just with some other randomly chosen token from the vocabulary. And then other times we're just going to leave the input word as it is, right? So like in this example, we want to predict 2. 2's in the input. We choose not to replace it. And so it's just there. It's like perfect. It needs to go straight through from 2 to 2. But because of these other corruptions, that might be a difficult thing to do. So this is weird, right? Like the idea here is to take this corrupted input and correctly predict the missing tokens in the output. So when you go to like your Hugging Face library and you pull out a BERT model to be, like your pre-trained model for doing some sort of natural language, you're going to fine-tune for some natural language task. That model was trained to do this task right here, this really bizarre task. Well, like, why should this work? there's something written here, but like, what's going on here?
I think the model should be able to reason the context, even though. So there are many components that like constitute the context of a sentence. So if we omit one, then there should be other components that contribute that context. So the model should be able to learn them.
Yeah, that's awesome. That's exactly it. That's really well said. There are lots of parts of the sentence that should go into a lot of context from the sentence that should go into giving you the correct prediction of the missing tokens. And by doing this kind of masking and this kind of randomization, you're forcing the model to do a couple of things. One is to use the thing, to use the context that it has to use, like it can't use the mask stuff. Although it can use the mask stuff in the sense that it knows that there's something masked there and it can try to deal with it. And this corruption, adds some noise here where again it's forcing it to disambiguate the actual context from the noise. It's going to see the same sentence, it's going to try to decode this a bunch of different times as you train like epoch over epoch. But each time it sees it, it's going to see it with different tokens masked and different like other tokens randomly replaced. And so it's going to force it to learn, and also like different ways in which you're going to need to predict, or different tokens you need to predict in the past. So it's going to force it, just on average, to really learn to use just the parts that matter for doing the task. Yeah.
So there's like masking happening and replacing happening, and from what I hear you saying, like the file has some sense of like what has been masked.
Yeah, because that token shows up all the time.
But does it not know like which word has been replaced? Like
right. It doesn't know. It doesn't know this. It doesn't. We're not telling it. So it knows what's been masked because like there's a mask token there, but it doesn't know. It doesn't know that this pizza is wrong. Like that it should have been masked.
So you're using this like a spell checker?
Well, yeah, it's a lot more. It's like spell checker in the sense that it's trying to use the context to give you the correct. The correct fill in there, but instead of doing it at the character level, it's doing it at the token level. So it's similar. I mean, obviously different technologies being used there, but yeah.
Like, would it be possible to try an idea from like denoising images, like in VIE, where
it's really close to that.
Do reconstructions?
Yep, it's really close to that, right? Like, it's close to that. Or it uses the same ideas by adding noise to here. You're causing, so it's going to be harder to learn the task, but it's going to be far more robust at doing the task because it's how to overcome some of these things. Notice too, like this would not work if like say the replacing happened like 90% of the time instead of 10% of the time, right? Like this would completely fail because like obviously that's too much noise. Like there's not enough signal left. But these are something like hyperparameters in terms of the training, and add just enough noise to make this. And I'm sure the optimal is not exactly 10%. It's probably like 11.7% for whatever for the particular corpus. But whatever. Like the point is that this approach really makes the final embeddings you learn of these words very, very robust. So yeah, so encoders on their own are trained using tasks like this. Let's see.
Sorry.
Yeah.
I have a quick question. So on what was on the last slide, it said that something would be replaced with a mask 80% of the time.
Right.
Why is that not too much noise? Or like, how does that? Because that feels kind of similar to like we've taken away so much. How is there anything left to learn?
Yeah, it's a good question. I mean, it is a lot. Again, that's like a kind of empirical result that works, and we're not actually showing it over here, like in this way. But yeah, like a lot of these get masked out. So what happens there is that it's really forcing it to just use the tokens that are not masked. So there's a lot of noise here. Like, the training of these takes a long time. I think one of the slides talks about it. Yeah. So training on this, on these really large corpora. Yeah, right here. 64 TPUs, so these specialized, chips for doing deep learning workloads for a total of 4 days. This is a massive amount of compute, like really out of it's hard to imagine actually what kind, like the amount of compute. Where like the rest of us are on collaboratory with our single like K80 GPUs there, trying to make sure that everything trains in enough time where Google doesn't kill our jobs, right? Like, so these things require a massive amount of compute for a lot of days. So that's why it works really in the end. Like if you're just to do this, just a little bit, it would have a hard time. All right. Okay. Yeah.
So it's still unclear to me how we train this model, because without the decoder, how do we actually generate those tokens? I mean, not
so, I mean, you literally supervise it. So like the loss for this example right here will be a classification loss for what you hear, so here and here.
Okay.
It's like there's a correct word that goes there, or token, I and the. And then there's going to be the combined, like the average loss of those two, average classification loss. Yeah. So it's supervised in that way.
But we need a decoder, right? Because otherwise, how do we?
No, we don't need a decoder. The decoder's job really is just to, like when you have the encoder and decoder together, this is really to do sequence to sequence, models, like produce one sequence after another. You're not doing that here. You're filling in the gaps.
This is just many to many.
Yeah, this is many to many, exactly. But it's not done in a sequential way. It's done saying, I'm taking the whole of this context here and making these predictions.
Okay.
And that's the point of it. Like you're using the encoder because the encoder doesn't have the autoregressive mask. So you're using the whole of the sentence to do these tasks. Great question. Good job. So BERT is also trained on a different task where it looks like this. You have 2 sentences and or 2 phrases, and the task is literally to decide if, like, you have the order correct. Like, one of these should follow the other. And if you put it in the other direction, it's like it doesn't make as much sense. Like, if you have a pronoun like this, this should follow having said what the noun is that's referring to it, and it's like those kinds of things. This was done in the original BERT. Turns out that like a subsequent work decided that this wasn't so important. But the original BERT was trained to do this task as well. We're running out of time, so I'm going to kind of keep pushing forward. We kind of went this already. These are pretty massive models, pretty massive training sets. And if you now take these things and you fine-tune them to these tasks from Glue, right? Like acceptability, the inference, the question answering, and so forth. You start with the large model, so this one has 12 layers and a whole bunch of parameters. You now have state-of-the-art performance on all of these tasks. So by doing this really crazy pre-training to figure out how to replace the missing tokens, giving all this noise on the input, this thing has learned amazing embeddings that can be quickly fine-tuned to do these other tasks, these natural language understanding tasks at state-of-the-art performance. So BERT was an amazing innovation at that time, and really it still is like the core of most natural learning tasks that people are doing. Like if after this class you decide you love deep learning, you go work as a machine learning engineer or scientist someplace, and you're doing natural language, it's almost certainly the case that you're taking a pre-trained BERT model, whether it's like literally this one or some variant, and you're fine-tuning it to do your task, almost certainly. Because this in general is providing state-of-the-art performance. We're really quickly running out of time. These are not so good for generating sequences for like the reasons we've already been talking about. There's an autoregressive part here. They're not learning to do that autoregressive part. They're learning to take the whole context and like the task itself is not really. The task are just like trying to decode or trying to decode, but trying to fill in the blanks in this noised up version of your sentence. It's just not one for learning this autoregressive produce the next token. There are lots of extensions of BERT. I was just mentioning this. There's a couple of them. Like Roberto's pretty popular. Roberto's basically exactly the same thing as BERT, just bigger, more data. SpanBERT has contiguous. It's trained to fill in the blanks for like many contiguous tokens or massive tokens, things like that. And these do extremely well on a bunch of other types of natural language tasks. For the last few minutes remaining here, I want to get to this. So why did we get away from doing the whole encoder decoder thing? Why don't we just do decoders and encoders? I don't know. There's like some simplicity to that, but you can try to make these work. The question is like, what's the right way to pre-train? Like these make sense if you want to do like language translation because you have sequence input, sequence output. But if you're just trying to do natural language understanding tasks on a single language, like why would you use something like this? But it turns out that you can use these kinds of things. The pre-training is kind of what you'd expect. Just producing the next, taking a long sequence of tokens, encoding some of those, and then producing the rest of them. So, not that it looks kind of like a combination of the other two tasks. But something that was introduced in 2018, or same time as BERT, in doing this task is to do something. It's kind of a combination of what we saw with BERT and then like the producing the next token, and that is you have inputs where you're going to eliminate some of the tokens. And then you are going to eliminate other tokens, not the same ones, from the thing you're trying to predict. And the task is to predict correctly the fill in the blanks again. So it has that same feeling of BERT where you're trying to fill in the blanks, but you're doing this in this kind of sequential way where there's information missing from the input task. And you try to deal with that in producing the output over here. So I don't know, like it seems kind of simple. Like I'm sure if you sit down and try to come up with a research program along these lines, you're thinking like, how can I use both the encoder and decoder? Like this is like one of the first things you probably think about. It turns out it's pretty powerful. These models are known as T5. T5 is something like text-to-text transfer. Text-to-text transfer something. There's one more T. I got 4 of the 5. I can't remember right now. But it turns out that like these encodings also like are really great and can produce some state-of-the-art performance on glue and related tasks. There's glue. There's super glue. There's some translation tasks and so forth. So like also pretty good. So sometimes T5 is used. What T5 can be fine-tuned to do really well is this question and answering. And yeah, so like the T5s are huge models. You can see we're getting into the billions of parameters now, 3 billion, 11 billion. GPT-2 had, let's see, anyway, there's tens of billions of parameters, or no, 3 billion, let's see. I have one of the slides here, but a couple billion parameters. So like these are getting quite large, like really, really large networks. ResNet has about 25 million parameters. So, these are an order or two magnitude larger, or 3 magnitude larger, and say like a ResNet 50. And they're doing, they're achieving state-of-the-art performance on very general like question and answering tasks. And importantly, like these are these tasks. What makes these question and answer tasks difficult is this open domain nature of them. Basically, meaning that you can ask very general questions that where there should be no expectation of like having seen anything about particular questions in your training sets. So there seems to be a lot of knowledge being stored in these parameters, and you want to produce the correct kinds of answers in the correct formats. All right, for the final minutes, we have 1 minute here, but I'll just say something about GPT-3. So GPT-3 is like GPT-2. It's just way bigger. It has I can't remember. GPT-2 now has like a couple million parameters. GPT-3 has 175 billion parameters. By the way, there's noise of like GPT-4 coming out pretty quickly. That's going to be, will have trillions of parameters. So like the size of these things is unbelievable. You have to like have a partnership with Microsoft, who gives you basically most of Azure to train these things on to do this kind of stuff. So these are massive, massive models. But GPT-3 is basically trained to do exactly the same kinds of things as GPT-2 and GPT-1 was doing, just on way bigger data sets. And what's interesting about GPT-3 is this few shot nature of it. And it's seen so many examples that it seemed like a lot of things like this, for instance, where again it's just learning to produce the next tokens. But if you give an input that has this kind of structure to it, it basically has learned to figure out what the structure is and produce like the French translation of whatever this word is right here. It's not part of the training objective at all. The objective again is just to produce the next token. But these things are so powerful; they have so many parameters, and that kind of training just works so well that it learns to do these kinds of things. And if you remember, this is sometimes thought of as like this in-context learning. So again, it's just trying to just produce the next token. But when it sees this kind of regular structure, in context, it learns to do the kind of meta task that's within this structure. So adding, correcting the spelling, doing this translation task, so forth. Super amazing. I don't know if it's super clear why it happens. It's just something really powerful to do. If you remember, like I showed you at the beginning of the course, you give it these prompts. So literally you're just going to put these tokens in. Parodies of the fantasy novel series Harry Potter in the style of various famous authors. By Ernest Hemingway, you started off, it was a cold day in Privet Drive, and a child cried, Harry felt nothing, and then it just produces the rest. And it produces has Harry Potter content, but in the style of Ernest Hemingway, and all it needed was for you to, in English, just say that's what you want. Again, the task here is only to produce the next token. It just has done it's seen so many examples that it somehow knows what Harry Potter content is and what the style of Ernest Hemingway is and how to adapt that from the text. And there's other examples here, if you instead had started with my Jane Austen or any of these other authors, you'll see that this is quite amazingly doing the task. And as I showed at the beginning of the course as well, this can do question answering just perfectly, without having to do anything different. You just give it a question, and it will usually produce you the answer. I'm using the word for, that's actually wrong. Like, there's a lot of ways this doesn't work, but, you know, it's seeing so much text, you can see a lot of HTML, so it produces like correctly formatted HTML and some kinds of things. So, really quite amazing. What GPT, so things coming out of this are like codecs that we talked about, I think we mentioned one time before, or like Copilot that might be in the VS Code, editor, where you write a doc string and it produces code that sometimes is actually doing exactly the task that you described in your doc string.